Inside a modern industrial facility, highly volatile, pressurized fluids are kept in a state of continuous motion and extreme temperature. Keeping this volatile process stable requires a primary brain known as the Distributed Control System, or DCS. The DCS reads continuous data from sensors across the plant and executes real-time micro-adjustments to valves and pumps to keep production running smoothly. But any complex control system is vulnerable. A power loss, a severe software bug, or a targeted cyber attack can cause the DCS to freeze or fail entirely. When the primary control system goes blind, an entirely dormant parallel network must instantly wake up, isolate the dangerous fluids, and safely shut down the facility before a catastrophe occurs. This secondary network is the Safety Instrumented System, or SIS. This diagram illustrates the defining engineering axiom of process safety. The SIS must remain physically and architecturally independent from the DCS. The safety system utilizes its own dedicated physical sensors, logic solvers, copper wiring, and power supplies. If the control and safety networks operated on the same hardware controller, a single fault would destroy the process regulation and the emergency failsafe simultaneously. The independent architecture guarantees the safety system survives the failure of the control system. To understand how this isolated architecture functions under pressure, we can track the exact timeline of an emergency shutdown, following the data from a physical chemical leak down to a mechanical valve closure. True industrial safety requires an entirely separate physical reality built into the plant, remaining dormant until the exact millisecond of disaster. The timeline begins with a physical event. A pipe seal ruptures, releasing hazardous gas into a processing unit. Catching this release relies on engineering decisions made years before the plant was even built. System designers must anticipate the specific laws of fluid dynamics for the exact chemical being processed. Gases behave by density. Lighter methane rises rapidly, while toxic hydrogen sulfide sinks to the ground. This dictates hardware placement. High-mounted open-path lasers catch rising flammables, while low-mounted point detectors sense heavy toxics. Flammable gas concentration is measured as a percentage of its lower explosive limit, or LEL. Reaching 10% LEL triggers a warning alarm, requiring operators to investigate. Hitting 20% LEL triggers an automatic executive action, shutting down the unit. Toxic gases require a different scale. Hydrogen sulfide is lethal in tiny concentrations, so sensors measure it in precise parts per million, or ppm, triggering alarms at single-digit levels. Engineers map prevailing wind patterns and run computational fluid dynamics models to locate structural obstructions. These massive vessels create shadow zones where gas accumulates out of sight. A $1 million safety system fails to detect a massive leak if sensors are mounted 2 meters outside the physical path of the gas dispersion. Once the physical sensor detects the gas, it does not immediately order a total facility shutdown. A false shutdown on a large-scale LNG facility causes immense flaring and restart delays, costing up to $10 million in a single day. To prevent false shutdowns, engineers use voting logic. Under 1 out of n logic, a single spiked detector only triggers a warning alarm. An automatic shutdown requires 2 out of n logic, where 2 independent detectors simultaneously confirm the exact hazard to trigger executive action. This logic is governed by the cause and effect matrix. This master engineering document defines the exact mechanical responses, like valve closures and deluge activations, that must occur when specific voting thresholds are met. Voting logic ensures that a facility only shuts down when a physical hazard is mathematically verified by multiple instruments. With the 2 out of n signal confirmed, data travels to the safety logic solver, a dedicated piece of hardware known as a programmable logic controller, or PLC. Unlike a consumer computer, an industrial PLC is ruggedized to survive severe vibration, extreme temperatures, and heavy electrical noise. The PLC processes information through a 3-step scan cycle. First, it reads physical inputs into memory. Second, it executes the programmed ladder logic. Third, it writes the calculation to output modules. The PLC repeats this cycle every 20 milliseconds. Upon calculating a confirmed gas leak, the PLC cuts a 24-volt DC signal to the final element in the chain, an emergency shutdown valve. Process control valves modulate flow by opening partially, but emergency shutdown valves are strictly binary. They are fully open or fully closed. They utilize heavy spring return actuators that mechanically force the valve shut the moment electrical power is lost. These safety valves sit fully open for years at a time. The primary risk is stiction, corrosion or mineral deposits causing the mechanical parts to seize together precisely when the plant needs them to close. To prevent stiction without halting production, engineers use partial stroke testing. The PLC commands the actuator to engage, closing the valve roughly 10% of its travel distance to prove it moves freely, before returning it to the fully open position. Every safety function in a plant is assigned a safety integrity level, cell 1, 2, or 3, representing its statistical reliability to perform when demanded. Routine partial stroke testing lowers the valve's mathematical probability of failure on demand, ensuring it meets its strict SIL rating. A mechanical failsafe degrades over time. It only provides protection if its physical viability is repeatedly proven through strict testing cycles. The logic we've tracked applies to a single processing plant, but industrial infrastructure often spans hundreds of miles of pipelines and pump stations. Distributed operations require supervisory control and data acquisition, or SCADA, while a DCS controls a localized plant. SCADA utilizes a central master terminal unit to pull data from isolated remote terminal units spread across vast geographical distances. Because SCADA covers so much territory, it relies on cellular networks, satellite uplinks, and radio telemetry. Connecting industrial control hardware to these wider networks introduces severe cyber vulnerabilities. The 2010 Stuxnet worm proved that malicious code could physically destroy industrial equipment by infiltrating these networked automation systems. The worm intercepted the communication between the PLC and the operators. It manipulated the physical logic commands to spin centrifuges to destruction, while simultaneously transmitting falsified, perfectly normal sensor readings back to the control room screens. In distributed automation, securing the data transmission network is an absolute prerequisite to securing the physical infrastructure itself. All of this sensor data, loading logic, and network transmission ultimately terminates in the control room, displayed on the human-machine interface. Human operators are the final bottleneck. If an operator misinterprets the data on the screen during a critical alarm, the millions of dollars spent on fail-safe hardware are entirely wasted. This comparison illustrates the problem. Legacy interfaces, seen on the left, are cluttered with 3D graphics, spinning animations, and constant bright colors. During an emergency alarm cascade, this visual noise paralyzes the operator's ability to find the true source of the failure. The industry standard known as ISA 101 mandates high-performance HMI design, stripping away all aesthetic vanity in favor of stark cognitive clarity. Under ISA 101, the entire screen uses a flat neutral gray background. Color is reserved exclusively for abnormal conditions, forcing the operator's eye to snap immediately to the only red element on the monitor. Raw data numbers are replaced with simple analog bar graphs that indicate process deviations at a glance, organized within a strict 4-level navigation hierarchy. To prevent fatal delays, the interface must follow the 3-click rule. An operator must be able to navigate from the top-level plant overview down to the specific diagnostic detail of any single component in 3 clicks or fewer. From calculating the fluid dynamics of a toxic gas cloud to isolating safety hardware, down to the exact shade of graying rendered on a monitor. True industrial safety is achieved by relentlessly engineering out every single point of human and mechanical failure.